What is the true nature of black holes? How do their immense gravitational forces shape the cosmos? What secrets lie in the heart of these celestial entities cloaked in mystery? And what does the existence of black holes mean for our understanding of space and time? Stay with us till the very end to discover the groundbreaking research of Professor Rinaldi that could revolutionize our understanding of black holes and potentially the very fabric of our universe. Are you ready for a voyage into the unknown? Let's dive in. To begin, let's delve into the fundamental concept of black holes. Black holes are captivating celestial entities that have captured the imaginations of scientists and sci-fi writers alike. But beyond the popular portrayals of all-consuming beasts lies a realm of nuance and mystery. Black holes evoke a sense of foreboding emptiness, a place where the laws of time and space become distorted. These invisible behemoths possess an incredible power, exerting an immense gravitational pull that shapes the cosmos. Born from the remnants of dying stars, they emerge when the combined mass of these remnants reaches a threshold 3 times that of our Sun, giving gravity the upper hand and birthing a black hole. These cosmic entities are astonishingly dense, their gravitational forces so strong that not even the light can escape. It is postulated that most galaxies harbor a black hole at their very core. Black holes manifest in 3 distinct forms: stellar mass, supermassive, and intermediate mass. The stellar mass variety, the smallest among them, ranges from 1 to 100 times the mass of our Sun and is born from the collapse of a star's core. Supermassive black holes, on the other hand, dwarf their counterparts in size, boasting masses millions to billions of times greater than our Sun. These cosmic giants grow by merging with other black holes and consuming stars, expanding their dominance. Intermediate mass black holes, as their name suggests, fall in between 2 extremes and are believed to eventually merge, contributing to the formation of supermassive black holes. Loving the video or learning something new? Smash that like button and don't forget to subscribe for more awesome content you won't want to miss. The significance of black holes extends beyond their role in explaining the peculiar motions of certain stars. They offer us a gateway to a new realm of physics, challenging our understanding of the universe. According to Einstein's general theory of relativity, matter distorts the fabric of time and space, giving rise to the force we know as gravity. Black holes, with their concentrated mass, possess a gravitational pull of unparalleled strength, putting Einstein's theory to the ultimate test. At the heart of a black hole lies the singularity, a point of infinite density. The immense forces at play in this enigmatic region have puzzled scientists for decades, leading to an ongoing search for consensus. According to Einstein's theory, matter drawn into a black hole loses its information and is obliterated. However, quantum mechanics challenge this notion, sparking a fascinating contradiction. Astrophysicists and mathematicians find themselves immersed in the quest to reconcile these 2 seemingly incompatible theories within the unique theoretical environment that black holes provide. From general relativity to quantum physics and string theory, black holes serve as practical laboratories for fundamental theories that seek to explain the inner workings of our universe. Contrary to popular belief, black holes are not actual holes, but rather supermagnets of gravity. Imagine a force of gravity so potent that it surpasses Earth's gravity, creating the illusion of being drawn into an abyss. Black holes are formed when a massive star collapses, compressing its mass into an infinitesimal point. The gravity generated by this immense concentration of mass gives rise to the sensation of a hole. For instance, a star as massive as our Sun could shrink to a black hole the size of a small city, a testament to its extraordinary density. This extreme compression is akin to reducing the towering structure of the Eiffel Tower to the minuscule dimensions of a grain of rice. Thus, the term hole describes the effect black holes have on their surroundings rather than their physical form. In reality, a black hole is a spherical region encompassing a central singularity and an outer boundary known as the event horizon. Black holes, cosmic phenomena, house an intriguing singularity, a point of extreme density, exerting powerful gravitational pull. This concentration of mass makes black holes unique, their gravity unmatched. The event horizon, the black hole's boundary, signifies a one-way journey towards the singularity. Misconstrued as a physical barrier, it is merely a point of no return. Within, the singularity engulfs everything, rendering the black hole dark, as light cannot escape its gravitational pull. Observing black holes directly is challenging due to this intense gravity. However, scientific advancements have enabled indirect detection. Radio telescopes and gravitational wave detectors serve as proxies, revealing their presence. Einstein's 1915 prediction of gravitational waves, ripples in space-time caused by massive objects' movement, was confirmed a century later when two colliding black holes' waves were detected by the Laser Interferometer Gravitational Wave Observatory, LIGO. Black holes often affect their surroundings. Their consumption of nearby gas, dust, and stars generates heat and radiation, detectable through advanced instruments. In 2019, the Event Horizon Telescope offered humanity its first look at a black hole showcasing a shadow in galaxy Messier 87. This groundbreaking visual reaffirmed the existence of these previously theoretical cosmic entities. Venturing into a black hole is a perilous endeavor, as the gravitational forces at play subject any object to a process aptly named spaghettification. The immense gravitational force stretches and compresses anything that enters into a long, thin, spaghetti-like shape. Escaping the clutches of a black hole is deemed impossible unless a theoretical counterpart known as a white hole exists, an entity that expels matter instead of absorbing it. Black holes and white holes might be connected by interdimensional tunnels called wormholes, providing a glimmer of hope that a black hole could potentially transform into a white hole over the course of billions or trillions of years. In such a scenario, time would appear to speed up exponentially, making the process seem instantaneous from our perspective. Intriguingly, an alternative concept known as gravistar has been proposed to replace the enigmatic singularities, all without resorting to unverified theories of quantum gravity. Unlike black holes, gravistars are believed to be filled with dark energy, the very force that propels the accelerated expansion of our universe. This dark energy prevents matter from crossing the event horizon, effectively keeping it confined to the outer surface. At first glance, gravistars resemble their black hole counterparts, but recent observations of merging black holes have cast doubt on the existence of these peculiar entities. As scientists delve deeper into the complexity of rotating black holes, they have put forth more grounded explanations for the existence of singularities. According to Einstein's theory of relativity, the spin of a rotating black hole elongates the singularity into a ring-like structure, potentially leading to the creation of a wormhole and a white hole that opens up to a new universe. However, the turbulent interiors of rotating black holes, combined with the centrifugal force generated by their rotation, give rise to an inner horizon, emitting high-energy radiation as a consequence. The existence of rotating black holes possess a fascinating challenge to our current mathematical understanding, but it is through the detection of gravitational waves that glimpses into their mysterious interiors are revealed. These gravitational waves, first detected in 2015, are disturbances in the fabric of spacetime caused by the cataclysmic collisions of black holes. They have allowed scientists to witness nearly 100 mergers of black holes, shedding light on their inner structures and pushing the limits of Einstein's theory of general relativity. Picture, if you will, a box filled with unknown contents. The only way to discern what lies within is to listen to the sounds it produces when shaken. In a similar vein, black hole collisions serve as cosmic earthquakes, generating gravitational waves that reverberate through space and time. By studying these cosmic vibrations, scientists can begin to map the intricate structures of black holes, unraveling the secrets hidden within their unfathomable depths and putting Einstein's theory to the ultimate test. Professor Enrico Rinaldi, a physicist at the University of Michigan and Riken, has been focusing his efforts on understanding the inner workings of black holes through the principle of holographic duality. This principle implies that black holes may not be three-dimensional as predicted by gravity theory, but instead could be akin to holographs, two-dimensional entities that convey the essence of a three-dimensional reality. Rinaldi's research relies on the combination of quantum computing and machine learning to simulate the particles involved in the holographic duality. He uses a concept called a quantum matrix model, which, with the aid of advanced algorithms, helps find the lowest energy state of the system representing the particles around a black hole. In addition, a type of AI technique called a neural network is used to solve optimization problems related to quantum wave functions, thereby allowing a more comprehensive understanding of the particle systems. As per Rinaldi, the interior of a black hole can be modeled using these quantum wave functions. He suggests that our entire universe might be a holographic projection of particles, which could lead to a consistent quantum theory of gravity. In his view, these events within a black hole are depicted as a mesmerizing holographic projection, challenging our conventional understanding of these cosmic phenomena. His work is a step towards realizing a quantum theory of gravity and understanding what lies inside a black hole. And you, what do you think lies within dark holes? Let us know your thoughts in the comment section below. And if you enjoyed this video, be sure to give it a thumbs up and subscribe to our channel for more captivating content about science and the universe. Thanks for watching.